Hello everyone. Today we are going to discuss the connectedness of the general linear group GL and R. So let me first introduce what is GL and R. Basically, it is the collection of all square matrices of order n over the field of real number. We can also take the field of complex number here instead of R, such that determinant of A is not equal to 0. Thus, GLNR is this collection of all non-singular square matrices of order n. So, before going to the connectedness, it is obvious that GLNR is a subset of Mn cross nr, which is the collection of all square matrices of order n over the field of real numbers. Real numbers. So now let me first introduce what is connectedness, and I am taking the reverse route. I will first introduce what is disconnection and what is disconnected spaces. Then I will come to the connected spaces, and I will also prove a theorem which will help us to prove many results, and which will help us to prove that GLNR, whether GLNR is connected or not. So let me proceed. So first I will introduce what is the disconnection of a topological space. Let X be any topological space. A disconnection, a disconnection of X is defined as a pair of two non-trivial subsets A and B of X, such that number one, A and B are open in X. Second, A intersection B is equals to phi, that is these two open subsets of A and B are disjoint also, and the last one is A union B is equal to X. So basically, what is a disconnection of a topological space? It is a pair of two non-trivial subsets A and B of X, such that A and B both are open in X, and A intersection B is empty, and A union B is the whole set X. So because A union B equals to X and A is open, implies that X is equal, sorry, implies that B is equals to X minus A, and A is open, implies that B is closed also. Similarly, A is also closed. So instead of A and B both are open, I can also write here A and B are closed in X. So we have a pair of two non-trivial subsets A and B of X, such that A and B are either open, both are open, or closed in X, and A and B are disjoint, and A union B is equal to X. So then we will say that A and B are the disconnection of X. Basically, what we are saying that X is equals to A union B, where A and B are two disjoint and open, or we can also say closed here because I have shown that earlier. So we have a disconnection of X. Basically, we are breaking X into two parts. We can say roughly this, and in the later part, we will see that the disconnection takes very stronger part. So we will discuss that later. So if a topological space X as a disconnection x equals to A union B, I will say. Then x is said to be disconnected. Okay, and if not, we will say x is connected space. Connected space. Okay, so what we have shown that I have given the definition of disconnection x equals to A union B. If there exists a disconnection of x, we will say x is disconnected space. Otherwise, x will said to be a connected space. Okay. Now, if y be a subspace of x, then y is said to be connected if y is connected with respect to the subspace topology on x. On y induced from the topology on x is connected with respect to the subspace topology on y induced by the topology on x. Okay, this is the basic definition of connectedness and disconnection, connectedness and disconnected spaces. So now I will move to the one of the very important theorems which will help us to very easily check whether the space is connected or not. It will also help us to prove many important spaces uh, connected or not. Okay, so I am going to the theorem. Okay. A topological space X is connected if and only if every continuous function every continuous function f from x to 0 comma 1. Instead of 0 comma 1, I can also take, sorry, it is minus 1 comma 1 if every continuous function from f from x to the space minus 1 comma 1 is constant. Okay, now we are going to prove this theorem. Basically, what this theorem is saying that a topological space X is connected if and only if every continuous function from the space X to uh, the space minus 1 comma 1 is constant function. So okay, so let us first let us first consider that X is a connected space. So now let f from x to minus 1 comma 1 be any arbitrary continuous function, arbitrary continuous function. Now we claim that f from x to minus 1 comma 1 is a constant function, is a constant function. This is our claim. For if possible, let f from x to minus 1 comma 1 be a surjective map such that f is continuous also. Okay, I have given. I am saying surjective map. It means f is not constant because there will be some element in x that is mapped to minus 1, and there will be also some element in x that will be mapped to the element 1. Okay, so which implies that there exist subsets a and b of x such that a and b both are non-empty, and inverse image of the singleton set 1 is equals to a, and inverse image of the singleton set minus 1 is equals to b. Okay, now because this is a finite set, every finite set is compact, and every compact subset of it subset in a topological space is closed. That means singleton set 1 and both are closed, and since f is a continuous function, it means a and b both are closed closed and it is very obvious that a intersection b is equals to 5. Otherwise, there exists x belongs to a and x belongs to b such that f of x equals to 1 and simultaneously f of x is equals to minus 1, which makes no sense, which implies that a and b are two non-empty, obviously also non-trivial subsets of x such that number one, a and b are closed. Second, a intersection b is equals to 5 empty set, and the third part is a union b is equals to x. That way we have find a disconnection of x, but we have assumed that x is connected, which implies that it is a contradiction. That is f from x to minus 1 comma 1 such that f is continuous must be a constant function. Okay, so what we have done that we have assumed that f is a x is a connected space. Then we have proved that every continuous function from the space x to the space minus 1 comma 1 is a constant function. Okay, so now we will do the converse part. Conversely, let us assume that every continuous function f from the space x to the space minus 1 comma 1 is constant, and our claim is x is connected. For if possible, let x is equals to A union B, where A and B are two non-trivial open subsets of sorry, I am taking closed subset here. Closed subsets of X such that A intersection B is equals to phi. Now let us consider a function, consider a map f from x to the space minus 1 comma 1 such that f of x is equals to minus 1 if x belongs to A and 1 if x belongs to B. So in this manner, I claim that this function f from x to minus 1 to 1, which is defined as f of x is equals to minus 1 if x belongs to A and 1 if x belongs to B, is a continuous function. So basically it is very easy to see that this function is continuous, because if I take the closed subsets of this topological space, that will be minus 1 1 and this whole space minus 1 comma 1 and the empty set, and the inverse images will be A, B, empty set and the whole space X, which all are closed, which implies that f is continuous but not constant, which is a contradiction. It means X is connected. So our theorem is proved. What we have proved that a topological space X is connected if and only if every continuous function f from x to the space minus 1 comma 1 continuous is a constant function. Now I will use this proof theorem, to prove to see the main results which we have written as a heading of this lecture. So now we have the space GLNR. A belongs to Mn cross n R such that determinant of A not equals to 0. Okay. Now consider the function. So basically we have defined what is connectedness. Now I am going to see whether this space GLNR is connected or not. Okay. Now consider the map determinant from m n cross n are to the set of real number. Okay, then we know that this map determinant is a continuous function. Continuous function. Basically, if we take n equals to 2 and we have a is equals to a11, a12, a22, 21, a22, then determinant of a is equals to a11, a22 minus a21, a12, which is in a polynomial form. That is, if we take any sequence ak converging to a, that is a ij of k will converge to aij. That will result as that this function determinant from mn cross n uh, to r is a continuous function. It is very easy to check because if this sequence ak converging to a, then determinant of ak will converge to determinant of a. This will give us that this function determinant of a is a continuous function. So now obviously the map determinant from glnr to set of real number is also a continuous function. Okay, now consider the two subsets. A is equals to, sorry, minus infinity to 0 and 0 to infinity. Okay, now subset of R. These two subsets of R are open in R, which implies that determinant of the inverse map of this, which I am saying A, and determinant of inverse of 0 to infinity, which I am saying B. These two these two sets A and B both are open in GL and R. So the first question which will come to our mind, that how these sets A and B are subsets of GL and R, because the what is GL and R? GL and R is A belongs to M n cross n R such that determinant of A is not equals to 0. Okay, then the elements which are coming this set A, which will be the uh, set of square matrices, every element of A will have non-zero determinant. Similarly, every element of B will have non-zero determinant. So A and B are two subsets of GLNR, and A union B is equals to GLNR, and it is very obvious to see that A intersection B is equals to 5, which implies that we have a disconnection of GLNR. Okay, now I can also form a function f from GLNR to -1 to 1 such that f of x is equals to -1 if determinant of f of a, I will say this determinant of a is less than 0, and f of a is equals to 1 if determinant of a is greater than 0. Thus, we have a continuous function f from GLNR to minus 1 comma 1, which is non-constant. It implies that GLNR is not connected. So this is the result we were looking. So we have proved that GLNR is not connected. So now I will leave a simple exercise for all of you, that to check the set ONR of all orthogonal matrices of order n, whether this set is connected or not. This is an exercise for us. Okay, that's it from my side today. Thank you, everyone.